We'll wait for a few more minutes and then we'll start since people are still joining. Okay, hi everyone. I am Lalit. I hope you can hear me. Can someone just unmute and confirm that if they can hear me?
Yes, sir, you are clearly audible.
Okay, that's great. Okay, so yeah, we'll be discussing uh, things related to week two lectures on the course Computer Vision and Image Processing. Okay, so what was done in week two lectures? Hmm? Anyone? What was done in week two lectures? What was the main aim do you think was for week two lectures?
3D transformations,
Okay.
then geometric camera models.
Before that, the lecture four started with what?
It was shaped from shading.
Yeah, from shading. So yes, so the week started with shape from shading problem where one would like to know the shape of the object given just a single image. Well, given just a single image, but the point is you need some extra conditions to make sure that you can solve that problem. And then it followed up with geometric transformations, which tells us about how different transformations affect the coordinates, whether that's in 2D or 3D or in general in any n dimension. Given that geometric transformations, it was moved on to the different projection models that generally used to get the images. And I think that's how the week ended. Okay, so we'll start with one question and then based on what theory backs up that question, we'll be discussing that. Okay. So yeah, so one important thing that I would like to discuss before even starting the set of questions So what were the so what is shape from shading? I mean, I gave you just one liner, but can someone slightly elaborate? What does it mean? Anyone?
Can you repeat your question?
Yeah, what is shape from shading? Can you just explain it? Not
From
the
the va-
process, but what's the aim and what are the major points out there?
from the variable levels of darkness, uh, we are trying to get the structure.
Uh-huh, okay. So yes,
Yeah.
since when we try to image an object, right, what we see is that not and the whole object doesn't have same color. Even if the object color is same, because of the lighting conditions, you might see that some part is reflected better than the other part. So what our basic assumption in shape from shading is that the intensity gives us some idea of how the shape is. If that assumption doesn't hold true, you can't go ahead with shape from shading problem. So that's the first basic assumption out there. And of course, to solve that problem, there were some other assumptions that were made, like it was Lambertian, the surface is Lambertian. What do you mean by Lambertian?
It's a diffuse surface.
Okay, anything more technical? I mean, yes, it's diffuse, but what do you mean by diffuse? So yeah, this definition was given in week one lectures about
Yeah.
diffuse and Lambert surface. Yeah.
Yes.
So anyone can tell me what Lambert means? Diffuse.
The radiance leaving the surface is independent of angle.
Leaving the surface, and that's it.
No, income.
Incoming direction. So yeah, both the incoming I mean the radiance, well, rather the reflectance doesn't depend on uh, both the incoming direction of the light or whether the viewing direction in which the light goes away. So it's independent of both of them. Then you call it as a diffuse surface or Lambertian surface. So any example of Lambertian surface?
Cotton.
Cotton. Okay, yeah. I mean, yeah, that's the example given in lectures. A few more were discussed last class, but anyways. Um, so one more assumption is that the albedo is uniform. So in the sense that uh, when you consider a surface, each point can have its own albedo. That means your BRDF can be different for different points, even though it is Lambertian. So the other assumption that was made during this shape from shading is that all points will have you same albedo, the row that was being taught in the class. So given that we can recover the normal information if we have enough constraints. Like someone pointed out that if we have multiple light sources and we keep the object and the camera fixed, we can try imaging the object from different lighting sources individually. We'll not switch on all the light sources at once, but we'll switch on every light source individually, and then we'll get a collection of equations which we'll solve to get the normal at that specific point. And once that is done, the final thing to get the structure is to integrate normals. So once that integration is done, we get a structure of the surface. So there is one more assumption that was mentioned in the class. What was that? Something regarding the surface. Of course, we discussed that it should be Lambertian and it should have uniform albedo. But one more assumption is there.
Uh,
proper word is not remembering, but it is like shine.
Okay. So we know the lighting direction for the problem. If you remember, the image intensity is proportional to the normal vector and the direction from which the light comes at any given point, at any given pixel. So we are trying to find normal vector, so we assume that our lighting direction is known. Okay, that is one of the points, but any other point? So we assume that the surface is smooth enough. If it's very rough, in the sense if there are too many discontinuities out there, uh, then it's very hard to model that using shape from uh, shape from texture, shape from shading. So if I give you a comb and I'll ask you to get shape from shading, probably that's a bad idea to get the shape of the comb because it has too many discontinuities out there. But if I give you a ball or a sphere, it's very relatively easy to solve that problem. Okay, given this, then yeah, so yeah, these are some of the important points that you should remember before even thinking of shape from shading in practical scenarios. Okay, so we'll start off with the first question, which is related to geometric transformations. But as I said, with each question, we'll try to discuss what's the whole topic behind it, and not just the question itself. Okay, so so what is this? A point 2 comma 3 is translated by 2 comma 1 and scaled by 5 comma 5. Find the new coordinates of the point. So do you think this is a geometric transformation?
Yes,
Why?
because first translation, then
Mhm.
it is followed by scaling.
Okay. So yeah, both the operations translation and scaling are part of geometric transformations.
Yes.
Yes, that's why it's a geometric transformation. Yeah. So there are multiple operations that will again come back soon enough in next few questions. So before we do this, we would like to know, I would like to know whether you got the concept of homogeneous coordinates. So what is homogeneous coordinates? Or rather, I'll ask this first. What are the coordinates given in this? The 2 comma 3, which coordinate does it represent?
X and Y.
Cart-
X and Y.
Cartesian
Normal
coordinate.
Cartesian.
Cartesian. Yes, normal Cartesian coordinates or what? Non-homogeneous coordinates. So how do you convert it to homogeneous coordinates?
Adding one more dimension.
And what should be the value in that dimension?
1.
1.
Okay. Okay. So if I write this point x as 2, 3, so if x tilde is the homogeneous equivalent, so it should be 2, 3, 1, right? So what do you think? Why do we need homogeneous coordinates? Any intuition behind it? Why would we prefer using homogeneous coordinates?
It describes the 3D shape of that object or image.
Uh, no, I just added one more dimension. That's it. There's nothing great to it. I mean, yeah, we have embedded the 2D point into a 3D space. So
Yes.
this looks like in 2D space and this one looks like in 3D space, which is fine. But why? Why do you want to increase the variables?
In machine learning, we know this because we have heard bias thing.
Okay, okay. Well, this is not specifically a machine learning course, so we'll come back to vision. What do you think? Well, there it makes sense mathematically. I do agree that, but for our purposes, since we are doing geometry, so anything geometrically speaking, what
In,
Depth,
this may be the intercept thing.
yes,
depth was
somewhat right. Yeah. Anyone else?
depth value.
Uh,
Rotation operation, if is there, then this particular will help.
no, no, not that's not the real case. So I'll give you a simple example, motivating example. I mean, it has multiple uh, advantages, but I'll just give you one example of why you would like to use homogeneous coordinates. Okay, so given that the general line equation in 2D is given like this, right? Y equals to mx plus c. So what are the coordinates here, x and y? And what are the line parameters here, m and c?
MMC.
These are coordinates, these are line parameters. Oh, and m denotes what?
Slope of the line.
And c is,
C is intercept on the y-axis.
yeah, where it cuts on the y-axis. So it's something like this. If you have a line like this, maybe I should change colors. My lines may not be straight, but I hope that you understand that it's a straight line. Okay, so yeah, this will be 0 comma c, and if you have some information like how much angle does it make theta, then m will be what? Tan theta, right? Everyone agrees with this?
Yes.
Yes.
Yeah. So this is the x coordinate, this is the x-axis, and this is the y-axis. Now, what if I say that theta is 90? How will the line look? Theta is 90 means what is the value of m?
Theta is 90. It will be perpendicular to x-axis, parallel to y.
Yes, that's geometrically you're right, but what will be the value of m?
M will be 1.
No, tan 90 is
Infinite.
infinite. Yeah,
Infinite.
m will tend to infinity as theta tends to 90. Okay, so this is a big problem. Now, geometrically, we understand that for m 90, for instance, this will have rather right theta is 90. This has theta as 90 degrees. The specific value of someone said that it will be parallel. This line is parallel to y-axis. But when you write it algebraically, you see that m goes to infinity. That means you cannot determine a value of y, right? So how to solve this problem? So if I write, you can write the line equation like this as well, right? I will put it as d to avoid confusion. Yes, I hope this is clear. This is very simple line equation. A, B, D, and I can write it as x, y, 1 dot product of two vectors. Is this clear?
Yes, yes, yes.
So now what happens? If theta is 90, we can, I mean, these have physical value, physical meanings, all these A, B, and D. But when theta is 90, it will make sure that you will get something like x equals to some constant, probably minus k or something. It will make sure that automatically. You don't have to worry about, okay, at theta is 90, you might want to change reverse the role of x and y so that you get an equation. So automatically you get all the things solved in this specific case. So with this, what we get is this homogeneous uh, representation. So that's why we would like to use homogeneous representation. They are more stable in some sense that you can represent all possible combinations of lines, for instance, in this 2D case, rather than depending on changing the conventions. Okay, so given that we have an idea of homogeneous coordinates now, so yeah, we'll come back to the question. We have a point 2 comma 3 and this homogeneous coordinates is given as 2 3 1 is translated by 2 comma 1. So what is your translation vector? 2 and 1, and scale factors are rather sx is 5 and sy is 5. So what is your transformation? Okay, I'll write transformation related to t. How will it look like given that x is in homogeneous coordinates? What is the size of this transformation matrix? So your transformation should look like this. Transformation of scaling multiplied by transformation respect to translations, and which is multiplied by the homogeneous coordinates. Well, multiply I mean the matrix multiplication, matrix vector or matrix multiplication. Okay, so what is the size of this homogeneous coordinate? 3 cross 1. What should be the size of this transformation uh, for the translation?
3 cross 3.
3 cross 3. Okay. And what should be for the scaling?
3.
Sorry, should be the same 3 cross 3.
3 cross 3.
Yeah, because our output, whatever output we'll get after transformation, should also be of
3
size 3
cross
cross
1.
1. Since the input is in non-homogeneous coordinate system, output should also be in homogeneous coordinate system. Okay, so given now, what should this transformation look like for translation?
1 0 2.
Okay, 1 0 2
1 1 0 1 3.
0 1 3. Is it 3? Why 3?
This is 1 1 1.
Yeah, 0 1 1 and
0 0 1.
okay. So does anyone have a doubt here? So this specific part is always identity for transformations related to translations. This is what the actual translation is given in the question, and the last row will always be 0 0 1. That's how you define translation transformation corresponding to the translation. Is this clear? I think it's clear. No answers. Okay, so what should be the transformation corresponding to the scaling factors? So now you know that the size should be 3 cross 3. What should be the transformation?
5 0 0.
Next row
0 5 0
and
0 0 1.
yeah, 0 0 1. So when it comes to transformations related to scaling, these are the transformation parameters that are being used. So this is Sx and this is xy. Okay. So now the final answer is just the multiplication of these three matrices. Maybe I'll write x tilde transformed, which is tr of s tr t into x tilde. So if you replace just the values out there, and our original point was 231. So yeah, this is the final answer. Once you multiply, you'll get it. Any doubts in this question? Okay, I think no one has doubts. Would be great then. Okay, so then we'll move on to the next question then. Okay, is this visible? Okay, scene point coordinate, that means what do you mean by scene point coordinate? It's the 3D point given to us. So a scene point coordinate x is given as 400, 600, 1200. Okay, is perspectively projected. Okay, we'll understand what perspective projection means into the image coordinates. So your image coordinates looks like this, 24, 36. And the camera's principal point is at coordinates 0, 0f. So maybe I'll write principal point as C for now, which is 0, 0f. So what is, so assuming that the aspect ratio of pixels in the camera is 1, what is the focal length of the camera? So before we move on to that, what is perspective projection? Can anyone say the basic idea?
The distant objects will appear smaller in case of this perspective projection.
Sorry, I can't hear you. Can you speak loudly?
The distant objects will appear smaller in this perspective projection.
Okay, yeah, that's a consequence of perspective projection. It's fine. But anything more on what perspective projection means physically?
No, sir, we don't know.
Okay, so maybe I'll just explain it in a brief manner. So what perspective projection means is you have a center of projection, right? So this is some center of projection, and you have uh, an object out there. Yeah, you have an object out here. This is an object, and this is somewhere the image plane where the image is being found. So what perspective projection says is that you have a center of projection. This is the center of projection. So all rays will pass through just this point, mathematically speaking. There is nothing more complicated to it. So if you have this center of projection, okay, and this is one ray which goes like this, and if you see the other ray which is going across like this, which is almost a straight, which is the straight line. Yeah. So this specific model is called as perspective projection, and this is used in the basic pinhole camera model. I think pinhole, yeah, pinhole was also discussed in the lecture, so we'll also get to that. So the basic idea of perspective means everything will pass through a center of projection. That's it. That's the basic simple idea. So given that we have this question, we'll first solve the question and we'll move to the pinhole model so that we understand why the perspective projection even makes sense. Okay, so a scene point coordinate is this. So this is if your axes are aligned properly in the sense x-axis. So there are some basic assumptions out there. Assumptions x-axis of 3D and 2D are aligned. And again, same for y-axis. Y-axis of 3D and 2D are aligned. And the third one is this z-axis. Yeah, the z-axis passes through the center of projection. So once we have this assumption set out there, we can now solve this problem. Yes, these assumptions were mentioned in the lecture briefly, if I remember correctly. Yes. Okay. So now given this z is the depth of the object, and which is 1200 in this case. And what is this? This is f. And what else do we have? Okay. So this is z and this is f. Now you, for instance, if this axis is x-axis, so we can have two solutions here based on which axis you choose. This is what? The object size in x-axis is 400. I'll just write it uh, object size OS like this, and this is what? Image size. This is IS, which is the image size. So given this, so now you can clearly see that there is similarity of triangles out there from which you can solve this problem very easily. So given the similarity of triangle, how does it look? Object size by Z equals image size by F. Do people agree? This by this equals this by this?
Yes.
Sir,
Yes.
uh, when light pass through the lens,
Yeah, yeah.
then it will have different wavelength components,
Hmm.
and at a very distinct point they will meet the center axis. Which plane you will call image plane then?
Okay. For this specific case, you don't have to bring lens. Uh, we are just considering that there is no lens out here. Simple projection. The model doesn't involve any lenses at this point. It is simple projection operation out going on there. We'll get to the lenses question as well, but for the perspective projection uh, model, this is all you need.
Okay, okay.
Okay. Yes. So now given this OS by Z equals to IS by F, so your F will always turn out to be IS by OS into Z, right? So what is the focal length obtained from x-axis? Fx is 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 what? 400? No, sorry. IS is what? 24.
20,
OS is 400.
400,
And Z is
1200.
yeah. So what is this? 24 into 372, right? What about Fy? Fy is 36 by 600 into 12, which is 72. You get same in both the cases, correct? And that's the assumption that's given here as well. The aspect ratio of pixels of the camera is 1. That means whatever focal length you should have for x-axis, the focal length should be same for y-axis. So the image, what the image is a square image, and this answer corroborates that both the focal lengths are same. Okay. Any doubt?
I'm sorry.
Okay, that's good then. So yeah, as I said, we'll just briefly look through the pinhole camera model. So does this look like pinhole to anyone? Pinhole camera model. So how does pinhole camera looks? So
A small hole will be there. Through the small hole, the light rays will pass.
yes. So we have a box thing like this. So that box is our camera. Given this, we have a very small hole here, and given that you have an object, for instance, probably a tree here, you would like to do what? You can just, the basic principle is you just pass rays through this single point, and wherever it images, you have the image out there in the reverse fashion. Yes? Do you agree?
Yes.
Yes.
In all camera model. So yeah, one of the things that we can relate here with lenses. So here there is no lens out there, right? So given this model, now you can easily see that all if this distance is f, and again assuming our three coordinate systems look like this, that x-axis and y-axis are aligned to the image plane axis and the z-axis passes through the center of projection, then what can you do? Again, we'll get the same equation. So if you go, for instance, this is x and this is y, and you can take this to be z. So this x and this x, wherever the point x is projected, for instance, this point will project here. No, opposite side. So this point will project here. This specific point will project here, right? So given that we have a similarity of triangle here, so x by f, small f, will give us capital X by capital Z if this point has x, y, z as coordinates. And again, similarly for y-axis point, I mean, if you have some point here like this, you can take this specific point here, this specific point here. Then you can clearly see that if you measure along y-axis, y by f is what? Y by z. So these are the basic uh, projection equations coming from pinhole camera model. Well, just similarity of triangles out there. So one important thing that we have here is this size. How big the size of the hole should be. What is the size of the hole called? Hello.
Or if size would be big, bigger, then focus will be on the center.
No, everything is in focus.
Means
I'll get back to you there as well. What should be the size of the pinhole? So, does anyone remember aperture?
Aperture, yeah. So it should be as small as, if the aperture is small, we get a clear image.
If the aperture is small, you get a clear image. Okay, but then what? If the aperture is very small, then you don't have any light to pass through, right?
Mm.
Although it says pinhole, doesn't mean that we can practically have pinhole size out there. So your aperture should be as small as possible so that you can increase the sharpness of the image. But then the other problem there is if you reduce the size of the pinhole, your brightness level will reduce. So you won't be able to see image out there if the brightness is very low. So there is always a trade-off between what should be the size of this aperture, or rather size of the pinhole out there. And this
So
specific thing
like
is called as aperture.
it's like iris of the eye, right?
Uh, you could think of it like that.
Yeah, the
But
pupil. So
yes,
when
yes,
there is no light, it will expand. So the aperture is large.
yes, yes, yes,
There is
that's right.
lot of light, it will
Yeah,
decrease.
yes. But these are mechanical things, so we have to manually change it in cameras. Or if you have a pinhole camera model, you generally don't want to change it. So yes, given that the aperture, I mean, ideally it should be pinhole size. So what should be the focus? Which part of the scene should be focused? So if anyone remembers that there is a relation between the depth in which the focus can be there with respect to the aperture, right?
Its background is blurred with a
yes,
Yeah.
yes.
Yes.
Center will be focused, side will be blurred. This.
Yes. So if you use a big aperture, then your center will be focused, or rather, whatever object is nearby, that will be focused, and far away objects are not in
Blur.
focus. But if I
Mm.
use very small, infinitesimally small point out there, which is pinhole, then what do you think should be the focus?
then object will be in focus.
Object will always be in focus, but the background,
Background will be also,
in,
it's better, clear,
yeah, it's clear.
as compared to the first.
Yes,
Like
yes, yes.
this.
So if your point is infinitesimally small, everything will be in focus, right? Yes.
Yes.
So you can check those slides on aperture. So it clearly shows that if the aperture is big, you have a small range of focus, but if your aperture is very small, the range of increases. So here, if we assume that it is very small, although practically you need to have some small size, but mathematically speaking, if it's just a single point out there, your focus is infinite. I mean, you can focus all the objects out there. So is this clear? Pinhole camera model. So this pinhole camera model uses perspective projection out there. It is based on perspective projection. And yes, you get this inverted image because your image plane is behind the camera optic center or this pinhole. Okay, so I think we can move on to the next question if no one has doubts.
Sir, I have a small doubt.
Yeah,
So is it true that image always forms on the focal length itself, at the distance of focal length itself?
image can be found anywhere, but if you want a sharp image, you have to make sure that your image is on the image plane is on the focal length. Image can be formed anywhere. It has
Okay.
nothing to do with focal length. Well, it has something to do with focal length, as I said that if it's not on the focal length, the image will be blurry.
Okay, sir. Thank you.
because there are multiple rays being the rays do not intersect at the image plane. If the rays don't intersect at image plane, your image won't be sharp, right?
Yes, sir.
Okay, yeah, great. So yeah, this is rather big question, big in the sense slightly more time consuming than the other questions. But it's a really good question to understand what affine transformation means. So you are given that for affine transformation, whether which of these are true and which of these are false. That's it. So we'll go one by one. So for affine transformation, three or more points which lie on the same line continue to be collinear after transformation. Is this true or false?
Yes, true.
It's true. Okay. How do you say that?
Affine transform in two-dimensional if we add value in the component, then y-intercept will change only.
Okay. Okay. Uh, there are multiple things which are a part of affine transform. So what are the different transformations which come in affine transform?
Translation, rotation,
Yeah, rotation, then translation. Next what?
A, the
Scaling. Okay. Next what? Two more operations were taught in the class. Well, actually, those many
shear,
operations make. Yeah,
shear,
shearing. Shearing.
Cheering, huh?
And then, hmm?
reflect,
Yeah, reflection. Yes. So all these combined, or maybe one or two out there, you can combine all of them, or you can have one or two of them, and they can. These are all a part of what affine transformations. So we'll look through one by one, as I said previously. So what is rotation? How does the rotation transformation look? So just to be clear that affine transformation can exist in any space. It is not specific to two dimensions or three dimensions. It's a linear algebra concept, which of course we use it in a computer vision course, but it's a linear algebra concept and it can exist in n dimensions. So given that, what is rotation? How do you define a rotation transformation which does rotation? So just to make it clear that all of these can be represented by matrices, right? So all of them have been represented in the matrices in the lectures as well. So what are the properties of rotation matrix? Hmm? So just I'll write it here for n dimension. We'll just discuss it in general and then we'll go to the specific. Well, the question is general itself. There are no, yeah, the question is general itself. It's fine. So yeah, what are the properties of rotation matrix? I mean, why do you say some matrix has a rotation matrix? What class of matrices are they?
It will be a symmetric
No.
matrix.
Uh, well, asymmetry means if you are talking about the way it's defined in the class, then all these matrices will be uh,
Yes.
n cross n or n cross 1 n plus 1 cross n plus 1 dimensions. You can write all these transformations in this n plus 1 cross n plus 1 dimensions for an n dimension 3D point out there. Not 3D point rather, for an n dimension point out there. So yeah, we'll stick to n plus 1 cross n plus 1.
Rotation matrix is represented in form of angle theta, sine and cosine.
Okay, that is for 2 dimensions. For 3 dimensions. For 4 dimensions. For n dimensions. So since we will go with this specific convention of n plus 1 cross n plus 1. So if I write rotation matrix R as Rn cross n, so here there will be n number of zeros. Maybe I'll just write a big zero here. So this is a big zero vector, which is n cross 1. This is 1 cross n 0, and this is 1. So your rotation matrix in the affine transformation will look like this. So if you can tell me about what this Rn cross n looks like in general, that would be good. So do you know orthonormal matrices? Does anyone know orthonormal matrix? This is coming from linear algebra.
Orthonormal,
Yeah,
it's not clear, but it's orthonormal vectors are perpendicular vectors to a point.
yeah, yes. So orthonormal matrices are, of course, square matrices, as you can see that written n cross n. So these are square matrices, and as someone said that they are perpendicular, meaning C1 dot
Dot
product
product will be 0.
C1 dot product with any other Ci is 0, or rather I'll write it at Ci dot product with Cj is equals to 0 for I not equals to j. Fine. So if you take any two separate columns, their dot product will be 0. Is this notation clear?
Yes, sir.
Okay. And then Ci transpose Ci should be
With itself will be
1.
yes.
I is 1 to n. Here I comma j both values from 1 to n, but I not equals to j. Okay, so is this definition clear of a rotation matrix? So that so when you multiply the column with itself, you get it 1. Rather, take dot product of column with itself, you get 1. But if you take dot product with any other column, it will turn out to be 0. So this is how rotation matrix looks like. And rather, I will call this as rotation matrix, and this is the rotation transformation, and not the matrix as. This is also rotation matrix by definition, but for our session, I would just want to make it different. So you have this rotation transformation, which is same as this, which contains a rotation matrix. Now the properties of rotation matrix are it's square. If you take dot product of the columns of different columns, it will be 0, but with itself, it turns out to be 1. So given this definition, yeah, this is how you can define a rotation transformation. What about translation one? Translation, we did it in question 1. How will the translation transformation look like? Hmm? Can you quickly check
In
question 1?
in 3 dimension it would be 1 0 zero one
Yeah,
first two column.
yes. So since we are talking about general dimensions, here it will be an identity matrix, some identity matrix of n cross n, and there will be the translation vector, which is n cross 1. Here it will be a zero vector, which is, sorry, 1 cross n, and there will be 1 out there in the last. So this turns out to be n plus 1 cross n plus 1. Yeah. Is this clear? So this is the
Yes,
identity.
sir.
Yeah. So the identity, this is the translation part. Okay, so what next do we have? Scaling. How does scaling look like? Come on. 2 dimensions, if someone remembers, it can just be extended like anything. What will be this part?
It
Should
will
be,
be
yeah, yes,
if you divide by something.
no. Should just be, I want the structure of the matrix. That's it.
Diagonal matrix.
Yeah, it's a diagonal matrix.
Diagonal.
It's diagonal of some SIs, for instance. So where SI is the scaling
Scaling
for ith
factor.
dimension, right? So this itself will be an n cross n matrix since it's diagonal of it. Well, I belongs to 1 to n. Is this fine? Shearing. Okay. How does shearing look like? So shearing in general can be complex, but if you just take two-dimensional equivalent was what? 1k 0 1, right? This is shearing along x-axis. So if you want to do shearing along a specific axis, ki, where I is the ith axis along which you want to take contribution for shearing in this uh, jth column rather, sorry, jth row. So what it will be 1 0 0 0, and you shear with the ith dimension, and others will be 0, and the other whole thing will just be identity. Do you agree? So instead of since we have 2 dimensions here, you're taking the contribution from y-axis to be given into the x-axis, right? So it will be something like this, x and y. This is how sharing was defined, right? But then if you want in general some ith dimension whose contribution you want in the sharing, then you will just keep ki in the ith dimension and rest all zeros. Is this fine? We're just extending this two-dimensional case to n-dimensional case. Yes? Any doubts?
Yes, sir. Clear.
Yeah. Okay, great. Last is reflection, right? So reflection is a complicated phenomena in the sense there are many things which In higher dimension, it goes complicated. Which axis to choose, how will it reflect, whether you choose an axis or whether you choose a full uh, hyperplane out there to take the reflection. So for instance, in 2 dimensions, you can take x-axis or y-axis to take reflection, but in 3 dimensions, you can take xy plane, yz plane, xz plane to take reflections, right? So things go pretty complicated. So I'll just write it as RE. RE is some matrix, such that determinant of RE is -1. This is our matrix. Okay. Is this clear? The definitions are clear. So I hope everyone knows determinant, what determinant is. Otherwise, they can just check it out. Simple. So yeah, given these things out there, what one so yeah, one more last thing that we would like to do before solving this question. Since we know, I mean, I want to keep all machinery at the same place, then we can quickly solve the question. So what do you think? Is rotation matrix invertible? Yes, no?
Doesn't it lose the property of Ca transpose Cj is 0
When?
if the matrix is inverted?
Why?
Because then Ca transpose Cj will be 1,
Why? No?
Ij will be inverted.
No. Invertible doesn't mean that you're taking a transpose.
Yes, sir, it is invertible. If you Gaussian elimination apply,
Yeah, that's a good
last
way of
row will
arguing.
be
Yes,
as it is, and R and cross n could be reduced to
yes.
by Gaussian method.
So if you try solving this, R transpose R should be I. R into R transpose is also I. So of course, the inverse of R is R transpose for our specific purpose of rotation matrix only, not in general. Just try solving this. You will surely get rotation. I mean, given that this is the definition of rotation matrix, you will get this as one of the properties out there. So rotation matrix is invertible because you're multiplying two n cross n matrix, and this determinant is not zero. That means it is invertible. Given that you have all these properties, R transpose R is I, R transpose is I. So this is invertible. So if this is invertible, the transformation is also invertible. Okay. What about translation and transformation? Is this invertible matrix? Can anyone say it intuitively? Yes, no? Should be invertible, right?
Yes, sir. When determinant is not 0, then it should
Yeah,
be.
determinant is not zero, it's invertible. But just intuitively speaking, do you see that it's invertible? What does
Yes.
translation means? I'm just moving a 3D point from one place to the other, right? So if I invert it means I'll just keep it back to the same location. Yes, it is
Yes.
invertible, right?
Yes, it is.
Yeah, it's invertible. Okay, great. What about scaling? Can I undo scaling?
Yes.
That means, for instance, if you zoom in an image and then you come out of the image, zoom out,
Yes.
you can undo it, right?
Yeah.
So it is also invertible. What about shearing transform? If I produce a shear, can't I undo it? We can undo it, right? So I'll write the equivalent invertibles as well. It will be R transpose 0, 0, 1 for rotation. For translation, what it will be? We just now discussed it intuitively. This will be minus T. That's it, right? This is the inversion of this specific transformation. What is for scaling? Will be diagonal of 1 by Si 0, 0, 1. So this is clear, right? The first three. Shearing, yes, of course it's invertible, not just because I say, but yeah, it's invertible. So if this is the case, then the invertible part, rather the inverse, will be 1, 0, 0, 0, and that's minus Ki. Instead of Ki, it will be minus Ki, and all other things will be same. This will be 0, 0, 1. What about reflection? Can you undo reflection?
Yes.
Yes, if you reflect the reflected part, you'll get back to the original point. Yes. So yeah, for reflection, I cannot really write a form like this for what is invertible, but yeah, it is invertible. Okay, so yeah, it's invertible as you can see that the determinant is non-zero. So it should make sense from there as well. So given all this machinery that we have just checked it now, we can just quickly go through the transformations. Okay, so combining all these transformations, I will write a final transformation, affine transformation in general looks like this, which I would just write it as AT01. I hope the dimensions are clear. This is n cross n matrix. This is what? N cross 1, 1 cross n. This is 1 cross 1. So the whole thing is what? N plus 1 cross 1 plus 1. So this is the affine transformation. And what else do we know? A is invertible, and thus this whole transformation is also invertible because this is again linearly independent row that we added here. So the whole so whenever someone says it's an affine transform, uh, you are sure that it can be inverted because all the constituent transformations can be inverted. Okay. Okay. So given that we have this idea now, we'll quickly start the question. Three or more points which lie on the same line continue to be collinear after the transformation. Yes or no? So I have points x and x. Yes. Sorry.
No, sir, it would be not collinear.
Okay. Why do you say that?
If you apply sharing, then
Mm-hmm.
yes.
Okay. We'll see that. Well, it will be collinear. That's the answer. I'll prove it why it will be collinear. So we have p points out here. Mm, yes. So I guess for this specific part, we have to assume that it's in two dimensions. I mean, we are considering two-dimensional points so that our affine transformation will look as a 3 cross 3 matrix. So if we assume that, then we can use the properties of line directly. How does line look like? If these points satisfy a line, then how does it look? L transpose xi will be some C constant, right? For all values of I. Agreed? So I can rewrite it in what way? If I want to write it in homogeneous coordinates, it will be L minus C xi 1 dot product of these two vectors. Is it right? Does everyone agree with this?
Sir, actually it is the equation of hyperplane now.
Yeah. It's an equation of hyperplane, but since we are going in 2 dimensions, it will be now an equation of line in homogeneous coordinates. Yes, that's why I
Yes, sir.
mentioned, yeah, that's why I mentioned 2 dimension for line. Otherwise, there's to remove confusion. Okay. So yeah, given this is line equation in homogeneous coordinates, what can we do? So we have affine transformation which looks like this AT01, right? And I told you that this is invertible. What if I do this? L minus C given this. So if I take transformation inverse into transform, what does this quantity look like? This quantity? Sorry?
Transformation, then again inverse, it would be identity.
Yeah, this will be identity. So I can always bring on a transformation like this, right? Transformation inverse into transformation, rather a matrix inverse into matrix. So this transformation for our specific case, since n is 2 dimensions, so we have 3 cross 3 matrix out here. This is what? 3 cross 1. This is 1 cross 3. Of course, this is 3 cross 3. Okay. So now given this, we will just rewrite it L minus C. I should write it as L transpose for notation consistency. I can write it as transformation inverse into this is transform. This is another thing. I'll separate these two things out. So this is a row vector out here, and this is a column vector out here. Okay. So given these two vectors, so this also represents the same line. Do you agree? In the transform coordinates. So what does this give us? TR of xi1 is, yeah,
Transformed image.
yeah, transformed point. I'm just given 2D points, not an image. So what will it look like? A xi plus t, and last row is 1. So I'll just write it as xi prime comma 1. Yes, xi prime 1. Yeah. So these are the transform points. So I replace this part with this, and now given the left hand side, I mean the other part, I would like to do it this way. So this is what L transpose minus C transformation inverse, right? So this is some other matrix which now transform L minus C whole transpose. This is inverse transpose, sorry. Does everyone agree with this? I've just written it as a matrix, or rather column vector transpose. Yes?
Yes, sir. Very good.
Okay, yeah. So what is this actually? So this is some, what, L prime C prime, right? L prime C prime transpose, which is L prime transpose minus C. Do you agree with this? I'm just multiplying a matrix which is TR inverse transpose with a vector LC. So it will give me some L prime and C prime. Yes?
No, sir. If you can
Okay. So if you want the exact expression, I will uh, go away with this thing. AT01 inverse. Inverse of this matrix looks like what?
mm, you-
So the first part will be A inverse. The second part will be minus A inverse transpose. This will again be 0, comma 1. You can just cross verify that multiplying this and this will give you identity. Okay. So given that this is inverse, now what? Now you do inverse transpose of this. Trans this into L minus C. So what does it give you? A inverse 0 minus A inverse transpose 1 times L minus C. What does it give you? The first element will be A inverse L.
minus C.
The second element will be A inverse. Yeah,
Yes, sir.
A inverse something.
Inverse
Oh, this
TL.
is transpose. Sorry. Yeah, this is transpose. A inverse T whole transpose because I'm taking transpose of this, right? So this, if I keep it here, it will be A inverse T transpose. I'll write it properly. So I'm just taking transpose of this inverse, right? So what does it give you? A inverse transpose whole transpose, right? So A inverse transpose whole transpose times L plus C, or rather minus C. So the second element is A inverse transpose whole transpose L minus C. Do you agree? So this will be a scalar. The upper one is a vector. So what I now say is that let us define L prime as A inverse L and C prime as, I'll just simplify this, L transpose A inverse T plus C. So can I write it like this? I hope this is clear, right? L and C. So you can always, this is the new line parameter actually, L prime and C prime. So
Yes,
given
yes.
this,
You.
yeah, so I'm just
Yes, sir.
written explicit forms of L prime and C prime. Given that you have this explicit forms, so what is it saying? So you can write the new line equation in the transformed domain as L prime transpose minus C prime times xi prime and 1, which is 0. So all this satisfies for all values of, well, all values of I. That means it is satisfied for all points, right? So this is the new line. So that means 3 or more points.
Sir,
3 or
what
more.
we want?
Yeah,
Yes.
what we want is this first part, right? 3 or more points which lie on the same line. So we assume that our 3 or more points lie on this line given by the parameters L and C. Again, continue to be collinear. That means all of them lie in another line after transformation. So our new line is given by L prime and C prime. So all of them again continue to lie in after transformation. Yes?
Yes.
Any doubts in the first part? Okay, then we'll do the second part. What is the second part out there? two or more lines which are parallel continue to be parallel after the transformation? Yes or no?
No.
Why? What do you think so?
Uh, if you rotate,
Yeah, two lines being rotated will give you the same, will still be parallel, right?
yes, sir.
Okay. So given, yes, we of course it's true. That's why I'm saying it's true. But we'll solve it. So how do you define parallel lines? L1 transpose.
Vertical
Sorry.
will be two planes to parallel if their perpendicular vector will be same.
Okay, that's fine. But since we are writing it in general forms, well, here this for this specific case, again, we are going for 2D transformation so that we don't have problem with lines, definition of lines. So L minus C2, X and 1. Do you agree with this? So what does this look? L transpose X equals to C1, and this is L transpose X equals to C2, right? Something similar to the case that where you have slopes similar, but your intercept is different, right? Both of them have same slope, different intercept. Fine. Given this, now we'll uh, yeah. So we have defined what parallel lines is. What we have to see is that whether with the transformation we have parallel lines are still parallel lines or not. Okay. So again, we know the transformation looks like this: AT01, and our inverse transform, since we have already computed, so A minus A inverse trans A minus A inverse T,
0, 1.
yeah, 0, 1. Given this, so did anyone verify by now, or rather it should be A inverse? Sorry, it is inverse, right? It is the correct inverse. You should verify it. Well, it is correct as far as I look. Okay, given this, what is it out there? Again, as I said, I can always choose to keep these things inside the equation, right? L transpose minus C1 transformation inverse transformation times x, since it's a line equation, then not a point, x1 equals 0. Again, this will be identity as we saw earlier. So what does this look like? Transformation inverse transpose L minus C1 whole transpose times this transformation into x and 1, right?
Yes.
So what is this? What is this specific thing? We'll just write it down. A inverse minus A inverse P 0, 1 transpose of this. So 0 will come here. A inverse T transpose, and this is what? L minus C1. It turns out to be what? A inverse L, and what? This is minus, again the same way that we
Eh,
found A inverse T. L transpose A inverse T minus C1.
Yes.
So now for the second equation as well, it will turn out to be same. This is for line 1 But if you see line 2, it will be the same, just that your instead of C1, it will turn out to be C. Yes?
Minus C2 at the end.
Yeah,
It
yeah.
will.
Minus C2 will come here. So given that you have minus C2 here, so what you see is that the first line parameters are still the same. Should not be minus. Sorry about that. Yeah. So the first line parameters are still the same. So if you read, yeah, and
Yes, sir. They are
this is the
parallel.
transform coordinates. So given that these are the same line parameters, they are parallel. Yes.
Yes, sir. Only Y is changed.
Yeah. Y-intercept will change. Y-intercept was different as well initially. And parallel lines remain parallel. Okay. What was the third part? The extreme points of the original set are mapped to the extreme points of the transform set. And do you agree with this or not? What do you mean by extreme points?
Extreme in the means matrix is those one मतलब n cross n.
No. What do you mean by extreme points here means the
Points on end.
2D. Yeah, the 2D points here. The 2D points, if you have a square, what are the extreme points on the square? The four corners.
Okay.
The rectangle will also have four corners. The triangle will have the three corners out there. So those are the extreme points. So what was the question? Yeah, extreme points will remain extreme points. So how can we prove this? So we'll turn a different way here instead of using A as a general matrix. Since we know what constitutes A, if we can say that each of these transformations maintain the extremities of the points, then we can say that yes, it's the whole composition of these transformations, which is the affine transformation in general, also maintain that extremity. Yes, do you agree with the idea? So the things that we have to check is for rotation, translation, what else? Scaling, shearing, reflection. Okay, so given for rotation, what does it look? I take a rectangle out here, and these are my extreme points. So after rotation, how will it look? These are x and y axis. Just assume that it's always written. So if you rotate these points, how will you look? How will it look? These are the 4 points. So rotation is always done from, what do you say, from origin. So given this these 4 points are there, it will probably map.
Rectangle.
Yeah, the rectangle will still be a rectangle, but it will now be tilted. Yes.
Yes, sir.
So if you call these points as A, B, C, and D, these are still the corner points, right? Given that your transformation is rotation. Yes. So we agree with this part. Next is translation. Translation is quite intuitive. It will still be the same, right?
Sir, if we apply this rotation on image and half image goes outside the plane and we apply inverse again, it would be not be same then.
Mathematically, we assume that the plane is infinite, so we
Okay,
don't
sir.
really worry about they are important aspects when you actually try to implement on a computer. But for the purpose of solving problems, we don't really worry about it.
Okay.
Okay. So this is translation. Everyone agrees that we have translated, rather shifted the origin by some distance. So translation also maintains extreme points, right? Agreed? Next is
Yes,
scaling.
sir.
Scaling is also similar, right? We'll just zoom in things. If you zoom in things, for instance, if your original size is like this,
Zoom out will also be same.
yeah, zooming in or zooming out, both will be same. You're right. So probably zooming in might look like this. Maybe zooming out look like this. But in both the cases, the extreme points will always be the same. So this is also fine. We don't have a problem with this. What about shearing? What about sharing? How does sharing look? If I share it with respect to, if I share the x-axis with respect to y-axis, the same example given in the lectures, how will it look?
If shear at left, then it would be
Yeah, it will look something like this.
yes.
So our x-axis will rather, it will also somewhat, yeah. So now instead of a rectangle, it's what? Parallelogram. Even with the parallelogram, you can see that the extreme points are still same, right? These are the extreme points and initial extreme points. I mean, whatever get maps here is still an extreme point. And last one is what? Reflection.
Reflection.
So if I reflect it with respect to x-axis, what do you think?
It will be on minus y.
It will turn somewhere around here, but then you see that the extreme points are still the same. Extreme points remain extreme points. So yes, so in total, yes, affine transformation preserves extreme points. Preserves in the sense the extreme points are still the extreme points, although their locations will now be different based on the transform. Okay, so this is the third part, and the last part of it is the parallelism is lost between original and transform object, yes or no? We already solved this, right?
In sharing, we saw.
Yeah, in part 2 we saw that parallel lines will remain to be parallel. So yeah, the parallelism is lost means it's false. Okay, so this question is done. Does anyone have any doubts? Took slightly long, but I guess we covered through the basics of all the different aspects of affine transform.
Sir, how I can get this, session if I want to refer?
Yes, I have given it to NPTEL team. They'll post it soon. The previous session I've given it already. This session also I'll give it tonight. So
So this was first out session, or previously also there was
this is
session?
second out session. This is related to week 2 lectures. So week 1 lectures was already done.
Okay, so I can get both, no? Because I was not
Yeah,
aware
yeah,
about this
yes, yes.
session.
You'll get
So
all the
from where?
lectures, or rather all the videos, and also this PDF, whatever I'm writing, you'll get as a part of.
Okay, okay.
I mean, it's already shared with NPTEL team. They'll share it with you. So
No, so through that portal I'll get, or you will going to,
no,
post
no,
on
through
Google
the
and
portal, they'll give you the links.
portal only.
Yeah.
But
Sir, in
when?
which section?
we will get the PDF of this, today's session?
That once they'll upload, I'll specifically mention that, but they haven't uploaded it there, so I'm still waiting for them to do it.
Because sir, means it takes time, no? So how
Yeah, I
means
understand. Yeah, but
yeah.
to be frank, I've done my part. I'm just waiting for them to uh, finish their.
Yeah, otherwise, I mean, if you can post in that, a question session, no, we have that forum, discussion forum.
Okay, yeah, I'll check with that whether I'm permitted to do it or not.
Yeah, kindly
There,
do,
yeah,
please.
I'll check with that. Okay.
So, this is not uploaded in YouTube, right?
It is uploaded. You can actually check the course number and you can get it. NOC23-EE39. The video will be available, but for PDF, you have to go through NPTEL.
Okay, okay. Actually, previously we were getting everything, the DAO session and everything in means YouTube.
Yeah, yes, I know. And previously also I took course and it was made available.
Yeah.
So,
So generally they used to do like means after session they used to post
hmm,
uh, here itself.
yeah,
So that's why.
yeah.
Yeah,
Okay.
actually previously also
Yes.
I missed, sir. So that's why
Okay,
I
no
wanted
problem.
to
I mean,
request.
the video will be there. I mean, you can just search for the course code on YouTube. But
All
PDFs,
right.
I'll make sure that.
You also, sir, please, if they permits, then kindly post in, that
Yeah, yeah,
ask,
yeah.
ask
Okay.
question session.
Yes. Yeah.
Yeah, thank you.
Okay. So we'll move on to the next question since we are doing transformations. Maybe one more small short question on transformation. So someone was saying about rotation matrix in 2 dimensions. Yeah. Okay. So we'll try this question. Given a line segment starting a point at 0 comma 0, so we have a point here at 0 comma 0, and the ending point is somewhere at 4 comma 4. How to We need to apply 30-degree rotation clockwise direction on the line segment and find out the new coordinates of the line. Okay, fine. So how do we do it?
First, we can convert it into polar coordinates then.
Uh, yeah, okay. So that's a good way to derive it. So so maybe let's derive it quickly. It will not take too much time. So given a coordinate x comma y and this
Cos theta and
line
sine.
and this line out there, what is it? Uh, how do you write the polar coordinate? So it will be this distance is r and this distance is theta, right? Sorry,
Yes, sir.
this angle is theta. Yes. So when you write the x comma y can be written as r comma theta. So where specifically speaking x is r cos theta and y
Cos
is r
theta.
sin, right?
Mm. Yes, sir.
Everyone agrees with that? Okay, that's good. And so what is to be done next? So since we want to move clockwise direction, given that we want to move in a clockwise direction, how does it go ahead? So maybe I am moving it by an angle alpha in clockwise direction. This is clockwise, right? This is theta, x, y. So this is my new point, x prime, y prime. This is my old point, x comma y. So what does this look? So my r is still the same, the distance from of that point x comma y to the origin. It's the
Yes.
same, right?
Angle
So
would be theta minus alpha.
yeah, so x prime is what? R cos theta minus alpha. Y prime is R sine
Minus sine theta minus
theta.
alpha.
Yeah. So what is it that we can do? We can just expand it, right? cos theta cos alpha plus sin theta sin alpha, right? And for y prime, our sin theta cos alpha minus cos theta sin alpha. So I'm using just the usual trigonometric identities out there. So what is it that you see? I have r cos theta here and r sin theta here. Here r sin theta and r cos theta. So maybe I can just write it in terms of my original x and y. X is r cos theta, y is r sin theta. So this is x cos alpha plus y sin alpha. Y prime is x. Did I do something wrong here?
Minus so cos A minus B, cos A, cos B minus
Cos A minus B is cos A
plus.
cos B plus sin B. And
Hmm.
sin A minus B is cos B. So r sin theta is y, right? Okay. It is what? Y cos alpha. Sorry. Y cos alpha minus x sin alpha. So I can write the whole thing in short as x prime y prime is what? Cos alpha sin alpha. This is minus sin alpha cos alpha times x and y. Do you agree with this?
Yes, sir.
Okay. So given this,
Yes.
what can we do? So given now we are just given the values out there, right? X comma y is one will be 0 comma 0, other will be 4 comma 4, and alpha is given as 30 degrees. So given alpha as 30 degrees, our cos 30 is what? 3 by 2, and 30 is half minus half root 3 by 2. So we have this transformation here. We need x prime y prime. For 0 comma 0, what it will be? The transformation will be just multiplication with zeros, right? So my x prime y prime will also be 0 comma 0. Yes.
Your origin will remain origin.
Yeah, the origin will remain origin. Yeah, that's great. The next, then if I take x comma y as 4 comma 4, what will be x prime y prime? Just multiply 4, so 2 root 3 plus 2. Okay. 2 root 3 plus 2, that will be the x coordinate, and y will be 2 root 3 minus 2. Yes, just multiplying here with 4 comma 4. Agreed? Any doubts in this
Yes, sir.
question? So yeah, these are the two extreme points of the neodynamics, the rotated lens. Okay. Okay. So the next thing is, so yeah, this is okay. So this is for clockwise rotation. What do you do with anti-clockwise? How will the matrix look like?
And
Can anyone say that?
angle will be theta plus alpha. Then
Yes, angle will be theta plus alpha. So instead of alpha, we can replace minus alpha everywhere here in this matrix. Yes.
yes, sir. Cos A plus B.
So cos of minus alpha is cos alpha, and sine of
Yes,
minus alpha is minus sine alpha. Yes.
yes, sir.
So that means it will be cos alpha minus sine alpha cos alpha. That's it for anti-clockwise. This is clockwise. Okay. Yeah, I think okay, this can be copied. So there are four options given to you. 15 centimeter object is placed 30 centimeter from a convex lens, which has a focal length of 15 centimeter. Which of the following option is correct? So you need to compute the magnification, right? What is the formula for magnification?
V by U.
What is B and what is U?
Image distance and object
I
distance.
Yeah, so it is like image distance or object distance. Negative, negative sign is there. Image distance by object distance. So you can, I'll just use the notations used in the class, di by do, or if you rewrite it, it is f by f minus do. So di is the image distance, do is the object distance, f is the focal length. So what will be here? You can just place the values out here. Focal length is 15 centimeters. This is 15 minus object distance, which is the object distance, 30 centimeters. So this 15 is the object size, and we don't really need it in the question. So what is this? -1. So magnification is -1. So either this option or this option is right. So what does minus
image
signify? Yes.
real. It would be real.
Yeah, for negative uh, magnification, the image is real. Yes. Why do you say so? Because the image distance is positive and the object distance is also positive. So if both of them are positive, that means the magnification is
Because
right.
in our eye it would be inverted, and I uses convex lens.
Okay,
Yes.
okay, that's fine. So if anyone remembers this, diagram looks somewhat like this. I have an object here, image here, so the object, image, and your lines will, two lines will go like this, which should meet the image like this. So this is the image distance, the object distance, and this is the focal length. Yeah, for this specific case given in the class, it is a convex lens. Yeah.
Sir, in this we are considering the light is monochromatic now.
Uh,
Otherwise, how we can say that image would be this plane or somewhat ahead of it? Because this lens would have different convergence for the
yeah,
different wavelength.
refractive index. That's what you're saying, right?
Yes,
Refractive index
yes,
now
sir.
will be different for different wavelengths.
Yes,
Yes,
sir.
for the purpose of question, you can think of it like the refractive index is same for all the wavelengths. You can think of it like that. Or else you, as you said, you can think like it's monochromatic. Both are, and both will work for this question. So for the purpose of solving questions, we'll try to make some simplified assumptions. Otherwise, it's impossible to solve these questions.
Yes, sir.
Uh, well, even in real life, when we do engineering problems, we have to take some assumptions. Otherwise,
And this is really the reason we have spectacles nowadays.
yes, there are multiple developments out there. Well, To be frank, I also don't know the true history of
Because
length.
the real reason for the spectacles now is because the books we are reading is only uses black and white color. If they are colored, then this problem will not be there.
Uh-huh.
Yes. If someone will do in this work, because I am facing same problem. I started using three red, green, blue colors. My
Mm-hmm.
vision is getting impaired.
Okay. Okay. Well, there are specialized lenses available out there in the market. Maybe in case you're having problems with your
They are not so good today because manufacturing is not
uh-huh.
happening.
Yeah, I understand that. Yeah. Okay. Maybe we'll move on to the next question. So we are given a transformation matrix. This is 2 cross 2 transformation. So instead of embedding everything into n plus 1 cross n plus 1, we are directly dealing it with n cross n transformations. You can, I don't want to confuse with that n or n plus 1. So this is just a transformation matrix. So whatever vector it will apply, the vector size will be 2 cross 1. And this is a 2 cross 2 matrix. So the transformation matrix gives us what? Pure rotation, reflection, shear in x or y. What is the answer? So we'll move one by one then, as usual. What are the properties of rotation matrix? So we take the columns. The dot product will be 0. First we'll check this property. So what is the dot product out there? 1 minus t square upon 1 plus t square, 2t upon 1 plus minus 2t upon 1 plus t square. This is the first column. And what is the second column? 2t upon 1 plus t square. This is 1 minus t square upon 1 plus t square. So what is this? 1 minus t square into 2t minus 2t. So 1 minus t square upon 1 minus t square whole square, right? Which is 0. Correct? Yes, no? Yes, no, I need an answer.
Yes.
Yes,
So
sir.
C1 transpose C1 will be what? Multiplying it with the same thing. So it will be 1 minus t square whole square plus 2t square upon 1 plus t square whole square. So what will this be? 1 minus t to the power of 1 plus t to the power 4 minus 2t square plus 4t square upon 1 plus t square whole square. So what is this? This is 1, right? Given these two things, it is a rotation matrix. Do you agree with this? It is always a rotation matrix for all values of t. Is it rotation matrix for all values of t?
No, sir, I'm not getting.
So what? So for the transformations, we have seen that everything should be invertible, right? So the rotation is also an invertible
Yes, sir.
matrix. So whether with all values of t is this invertible or not is my question. How to check that? Determinant of this given transformation should when does
Would
it go
be
to 0 is what we need to check, right? So we'll multiply these things. It is 1 minus t square whole square upon 1 plus t square whole square. This is minus and minus plus, okay, plus 4t square upon plus t square whole square. So the denominator can never be 0 for any value of t in real space, right? And what about the numerator? 1 minus, sorry, 1 plus t to the power 4 minus 2t square plus 4t square. And the denominator is 1 plus t square square. It is actually 1 for all values of t belonging to real numbers. Yes?
Yes, sir.
So that means the determinant can never be 0.
So it is invertible.
It is invertible. That means it will always be rotation matrix because we cross verified these things, the properties of rotation matrix. Okay, so given that it is a rotation, is it reflection? The determinant is 1. Can it be reflection?
Sir, rotation matrix, it is given A matrix that you are representing, and
Yeah, the A
last
is
row.
specifically here as T, given as the matrix T in the question.
Okay, sir.
So is it reflection? No, right? The determinant can't be -1. We have proved that it's 1.
Yes, sir.
So it's not a reflection. Is it shear transformation in X? No, neither in X nor in Y, because they look like this. For X, it will look like this. For Y, it will look like this. This is shear X, and this is shear Y. Yes?
Sir, if T would be 0, then
Yeah, then
it will be 1.
if T is 0, then it's identity.
Okay,
Is
in
it?
general, it would be.
So if T is 0, then it is identity. So K here should be greater than 0 for shear to happen.
Okay,
Or
no
rather, K
translation.
should not be equal to K should not be
Mhm.
equal to 0. That's all.
Okay.
Okay. Uh, okay, then I think I'll wrap up today's session with this question. We'll meet same time next week for
For next session, you tell some topics so that we would be prepared then.
week 3. We are
Something.
just going sequentially. Just go with week 3 lectures and maybe just try to do some more mathematics behind the lectures, not just uh, the things out there, so that you can understand deeply now. Because half of the things that I've taught here, or rather we have discussed here, is mostly in linear algebra, but they are useful in computer vision. So maybe just try to see the prerequisites for that specific week lectures. It will help you, well, help every one of us to go through it.
Well, for this positional transform, we have matrices, but for if we discrete transforms, then how we get the matrices for them?
I did not get you.
Means there are various types of transform there.
Hmm.
Uh, how they get the transforms actually? So,
Various types of transforms means, so in our specific case, today we have just
so
discussed. Yeah.
we consider discrete cosine transform.
Oh, those transforms. Okay. So they
Yes,
are
sir.
different transforms. Yeah, they are also transforms, but they are different kinds of transforms. What we are discussing is just in the class of affine transforms and whatever came here as is. Yeah, they are there. They are used to manipulate on the data, whether, I mean, whatever dimension data it is, 2 dimension, 3 dimension. That's why generally you do it for 1 and 2 dimensions. But those, yeah, you have to look into other lectures, I guess. I don't know whether it's a part of this course or not.
Okay, sir.
Yeah, okay then. We'll
Sir,
see.
first we design the transform, then we saw the properties of the transform, or first we we have in mind the properties of transform, then we design the formula.
Uh, so if you ask me specifically, all these transforms, whatever Fourier transform, cosine transform that you have said,
Yes, sir.
they are coming for a specific. I mean, they have come because there are applications related to it.
Sir, if you take just if you take discrete cosine transform, it has property that lower
Yes,
would be
yes, yes, yes.
lower thing would not change the image too much. If you update in upper part, then it would be reflective directly.
Mm-hmm. Yeah, yeah.
Sir,
So you are
that
asking whether that property comes first or the transform comes first,
yes,
right?
sir. Yes, sir.
Well, I don't know the history to be frank, but at least for Fourier transforms, I can clearly say that they were developed to analyze the systems,
For
and that's how
it can be proved, sir. It cannot be proved by the formula only or anything.
it can be proved by formula. If I
Yeah,
if you have some assumptions, it can be proved with formula, specifically for discrete cosine transform, what you're asking. But there should be
there
some
are
specific assumption.
thousands of
Yeah.
transform.
Sorry.
There are a lot of transforms
Yes, yes,
which
there
to
are.
use when
Which to use when is something depends on your application. So not every transform is suitable for all kinds of application. That's what I can say at this point.
okay.
Okay, I'll see you guys next week. Okay, thanks for joining. Good night.
Thank you, sir.